Thank you, Nicole. I think, so I want to start out because there's a couple things that you brought up that came to my mind when you were talking about agriculture being a big part of the land and then converting over to development. I'm getting to that age. Well, first of all, I grew up in Wisconsin.
Yes.
I have a lot of dairy farmers in my family who didn't agree with my career path, and so I spent a lot of time arguing with them over the years. And one of the things they said to me was that agriculture is such a big part of this country. If we start losing that way of life, that land goes back, or will be developed. You know, and we were way out in the country at the time, and I thought, that's not going to happen. Well, then from Wisconsin, I went to Wyoming and worked for a number of years, and I heard the same exact thing from the people that were working in Wyoming. I got married in Wyoming, and my wife and I moved out here. So now when we travel, we go back to both Wyoming and Wisconsin, and I see it happening. The land isn't going back into forestry. It's not going back into wilderness area. It's going into development. So when we say that the ag community is a steward of the land, they really are. And having a viable business that can also meet water quality standards and be in harmony with the watershed is really important, because the option is impervious surface, stormwater runoff, and development. So before I forgot that, I just wanted to throw that out there. Not that I'm that old, but it is something that I can see. Okay, so a couple of years ago, we were asked to come up to this area and start an effectiveness monitoring project based around all of the different efforts that were going on in the watershed. So there's not just here in Bertrand or the Nooksack, but all over the state, all over Washington, all over the country, we're spending enormous amounts of money trying to restore water bodies, and protect water bodies. And when I started this position 8 years ago, I was asked to come in and set up a program that monitors the effectiveness of everything that goes on in these watersheds. The problem is that there was no data to use to compare with. So most of the time we come into these watersheds after the fact, after 10 years, 15 years, $20 million have been spent, and then we were left with the task of answering that question, whether or not things were effective. The problem is the answer really isn't that easy. There's a lot of these things take a long time to measure, and from a water quality perspective, you need an awful lot of data in some cases to be able to answer that question, whether or not, even if things improve. So that was one of the efforts that we came into this watershed, or one of the ideas that we came into this watershed, knowing that it takes a long time to get to clean water, knowing that we cannot just focus on one parameter and use that as our benchmark. So what we've done is one of the first things that we do when we come into watersheds is we walk into the office of the conservation district and try to get cooperation. Nicole is very energetic and excited. I'm very energetic and excited. So when we start talking, it's basically, it's like, oh yeah, that sounds like a good idea, let's do that. And then all of a sudden we have a whole list of things that we have to do. And then I go back to Olympia, and then she goes back to her. But one of the ideas that we wanted to have is have more of a holistic approach. Not just look at water quality, but also look at habitat and biology in the watershed. And so we have a bunch of different monitoring types, and we have a bunch of different questions. What's the status of the water, the biology of the whole watershed? Another thing that I'm really big on is that as long as we're going to be in the watershed investing all this time and money, I don't want to leave the watershed and unless we have answers to some of these questions. If we do find problems, what are the problems? How can we fix them? Who can give us information to that can make that happen? And that's one of the things, one of the main reasons why we work with conservation districts so closely during all this. The second, at the bottom here, I talked about trends, conditions improving over time. And that really gets to the heart of setting up a study design, setting up a monitoring plan so that at the end you know you're going to have enough data to be able to show improvement happen. One of the things that I get so jealous of is when I look at the districts, not just Whatcom, but the other districts, they're sort of the success stories where I see these beautiful riparian areas, all this habitat improvement that's been done, and then I get to the end of the page and it's like, where's the data? I want to see some data because I know it's making a difference. But again, we just have to be careful about how we set this up and collect the data in a way that we can measure cause and effect over time. So, I see that change you over there, but I don't see it change up here. That, and I've never seen that before, so. Oh, there it goes.
Slowly. You talk, I'll fix.
This is the
This
way
second,
my brain
you
works.
keep talking, I'll get it.
One of the reasons I came to Ecology was because I worked for EPA back in Minnesota for a long time, and I worked in Wyoming for over 10 years. And in both places, I had always heard about how great the Department of Ecology was in Washington. So I picked up my family, my wife, moved away from all of our in-laws. I thought that was a good idea until we had kids. But we made huge sacrifices to come out here, and it was because I wanted to work for the Department of Ecology, just because of the reputation they have. So one of the things that we're doing with this study design is we're leveraging two different groups in our agency that go out and monitor water quality across the state with various different parameters. And then we also have another group that specifically goes out and looks at habitat and biological conditions around the state. Now they both do it in such a way that it's more site specific. They're not incorporated into any study per se. They're basically trying to answer statewide questions. How's habitat? How's biology? How's the bugs? How are the salmon doing across the state? What does the water quality look like? So this is actually important, and it actually gives our study more strength to it, because we, by incorporating the things that they do at a statewide scale, at a study scale, we're able to leverage that information they collect across the state. And then we can also compare what we see here with results that we see elsewhere. And we can do the same thing when looking at different land uses and different land use practices, as long as we keep track of them. It's just a delay. I just have to slow down a little bit.
Just have to be patient.
So we just had a really good talk about land use and what things look like here on the landscape. So I'll just kind of briefly run through this. Everybody knows where we are. Just on the U.S. side, we have I think 20.4 square miles of drainage, 25 miles of waterways, 60 miles of creeks, 7 miles of ditches, and this is the big one. It's 1,567 individual parcels. That's 1,600, around 1,600 individual people in the watershed that are all living here and working here and can make a difference of what's going on in this watershed. One of the issues is One of the difficulties is we do have problems in the watershed. It's also around 1,600 individual parcels that you have to look at and figure out whether or not improvements can be made, or whether or not I lost my thought. Just keep going. So it's a lot of people. It's almost overwhelming. So one of the things. Oh, there it goes. Okay, so this is a land use. This land use based on parcel for the overall watershed. And basically, it's a mixture of different types of agriculture. The darker areas are the more dense urban areas. The white areas here that she was mentioning are the residential plots. And here's sort of
Keep talking.
I'm just gonna.
Just
Oh,
keep
there.
talking. It'll come up, you just keep talking.
I don't know,
Think ahead.
it's my cue, so I know what it is to do next. So I'm going to talk about the next slide, and as long as I just keep pressing, so I know that it's going to happen. So one of the ways that we set this study up is we established 2 monitoring locations, one at the top of the watershed at the Canadian border, and one at the bottom of the watershed, where we have real-time flow gauges set up, along with continuous monitoring of different water quality parameters like nitrates, DO, pH, temperature, and rain. And the lower station here is actually the part of the Ecology station. We added our continuous monitoring of probes at the Canadian line, where USGS currently has a flow gauge already. And what we're looking at this area here, in between the 2 stations, what we call our treatment area. This is where things are happening. This is where our improvements are being made. This is where restoration is happening. So the idea is that we keep track of what's going on in this area, and then we compare it with the data that we're getting coming into the watershed and leaving the watershed. And then over time, as we increase the number of VMPs and habitat improvements, we should be able to see how those change in our water quality stations. But since there's so many different parcels and so many different land uses within the watershed, what we've done is I did that broken.
You broke it.
Basically what we've done is we've sort of broken the watershed up in between our 2 sampling locations, and we're doing what's called, what we call synoptic type monitoring. It's where our watershed folks come in and collect habitat, biological, and sediment samples in between these different breaks in land uses, in between our 2 main sampling locations. So basically what I've done here is I've just decided, okay, probably the most important places that we're going to do, that are going to be affecting water quality are within a certain distance of the actual water bodies. So I just basically clicked the land use parcels, land use map. I clicked 100 meters on each side of the corridor, and that reduced the number of parcels that we need to pay attention to from 1,600 to 930. It's still a lot, but it just at least gave me a sense that we're making a little bit, we're having a little bit more focus on where we're going to look. And this is just a picture of our habitat and biology working in the watershed. So, we'll just go right into results. So, the information here on the left side of the graph is an average of the 4 habitat biology sites that we've done in the Bertrand, an average. And what I've done here is I've pulled in data from similar streams that we have collected data from along the Puget Sound. So when I say similar, I'm not talking, there's nothing similar to the Bertrand or even to this entire watershed. But what I've done is I've isolated this data based on elevation, stream size, and land use. And so basically what you see is that all of the stations here in the Bertrand actually fare better as far as canopy cover as most of the streams that are monitored in the Puget Sound. The same thing. First of all, I need to go back for a second and say that when we do these habitat biological assessments, they take approximately 1 day per site. But then with all of the information that we get, we're able to calculate some 550 different habitat metrics. Each one of those habitat metrics relate to some sort of stream measurement, like canopy cover or cover for fish. And so what I've done is I pulled a handful of these metrics out that I thought were important and that actually worked really well in doing this comparison, and that's what I've got presented here. So the second metric that I'm showing you is fish cover, and it's basically anything that provides cover for fish. It could be vegetation, it could be logs, it could be undercut banks. A lot of times you don't even know the fish are there because the cover is so good. So all of the sites in the Bertrand actually were fairly consistent. They were on the upper 90th percentile of what we've seen in other streams of the Puget Sound. Now again, I'm telling you, this is the average for the 4 sites. It's not, it doesn't represent everything that's going on in the watershed. But if we go back and look at the habitat again from more of an aerial view, you can see that there is a lot of consistency here within the watershed, at least on the main stem. Another habitat metric that will come up here in a second would be woody debris. I know I spent my entire life thinking that wood in rivers was bad and we needed to get rid of it. But since I moved out here, I realized that it is an important part of the ecosystem, and it relates back to a lot of those metrics that I just presented, including fish cover, and also we can see in a minute here the sediment transfer. There's a big role in sediment transfer. So, anyway, so the woody, just look at my so the woody debris in Bertrand Creek, the mean was actually higher than what we've seen around in the Puget Sound, but the variability between the stations that we collected the data was fairly high. And when you go back and look for the reason why that is, you see that there's a couple of sites that have so much woody debris to bring the average up to the entire stream. And one of those places is right here in the park. The second highest concentration of woody debris we saw in the upper watershed, but it was still quite a bit lower than what we see in the park. And then when you think about what are the sources of woody debris, it's sort of interesting that we're seeing a lot of woody debris in a place where we have old growth forests. The riparian area, I guess, is fairly old. So you've got branches and whatnot, and deadfall falling into the creek, and it shows up in our data, and we're able to see.
Yeah, I can just mention something there. So the old growth portion is not right next to the creek, it's just a little ways to the west. It
It's in-
starts over
it's
here,
in
but
the
it's
back.
not that second growth, but it's, you know, we probably left a few trees right along the stream, just because it's got those ponds.
Well, and the corridor itself is it's so vegetated that it's and I think that was just what was interesting. It's like, where is that? Why is there so much more wood here in the park? So the next one was pool depth, and not only are pools important for fish, but they're also important for people to recreate. One of the highest pool depths, again, was right here in the park. And if you think about why that is, there's a big relationship between woody debris and pool depth. And when that wood comes in the stream, it falls in there, you have all kinds of different dynamics going around that wood debris making these pools. So anyway, where I left off, this is habitat results from the Watershed Health Assessment that we did in 2014 on 4 different stations in the Bertrand watershed. I left off on pool depth. Pool depth was the mean pool depth of the sites we looked at was still higher than what we observed in the Puget Sound, but there was a little bit more variance in data. And one of the reasons why there was variance in the data was because of the, again, at River Mile 6.8, which is right here in the park, we had a relatively large number of pools that were relatively deep in comparison. And I was making that relationship between the amount of woody debris and the amount of pools that we see in streams. And yeah, I think this is off.
Too fast. It's vertical.
Two of the other metrics that we get during our watershed health assessment, one is called relative bed stability, which is basically the overall stability of the stream bed and its potential to erode. We had a really high relative bed stability at the upper site and relatively lower bed stability at the lower site. When you look back at one of the big drivers of that, it's the percent of sand and fines that we find on the bottom of the stream. Now, I don't have any context as far as what we would expect to see in the stream, because I know that it's a relatively low slope from up to down. As a matter of fact, I think at the Nooksack, it's maybe 20 feet in elevation. So basically what I've seen that the bottom of the stream described that there are cobbles and gravels in the upper watershed, and the retreat and advance of the glaciers have pushed a lot of fines and sands to the bottom of the watershed. And given the fact that we don't have a lot of slope, this may be something that's expected, especially at the lower portions of the watershed. But again, I don't exactly know yet. This is something we'll talk to other people about and look for some other data. One of the other things I mentioned is part of this assessment, we're doing a lot of biology. We do macroinvertebrates assessments, and we compare that data to data we've collected at reference sites all over the state to be able to say whether or not the macroinvertebrate population is healthy. Something else that we do is we've been looking at the paraphyte community, which is basically all the algae and other slimy things that grow on the bottom of the stream. We do that as part of our watershed health assessment, but we've also set something up because they're such important drivers of what occurs in streams as far as chemistry, dissolved oxygen and whatnot. What we've done is we've set these paraphyte samplers up at some of the key, basically we've set them up at all the bridge crossings. And this way we're able to monitor not only the taxonomy of what's growing on there on a monthly basis, but we're also looking at the what effects they're having on nutrients, what effects they're having on metals in the watershed. And I'll go through a couple of these results really quick. So the top graph is called Algae Biomass, and it's basically a description of the amount of algae that's growing in the bottom of the river. This data represents these paraphyton samplers that were put in the month of July, and then taken out again in the month of August. So you can see we have the highest algae biomass at river mile 10.2, which is at the Canadian border. It drops to river mile 6.5, which is here in the park, and then the algae biomass goes up again once you go downstream. If you look at the nutrients in terms of phosphorus and total nitrogen in paraphyton, you sort of see the same parameter. It's high at the upper watershed, it drops again here in the park, and then goes back up. Which is sort of show you exactly where we are talking about this. Sorry about that. So another thing that we've been doing is we've been looking at metals and paraphyton, and this is part of a larger sort of statewide study that we have going where we're trying to associate metal concentrations with different types of land uses. And so we include the metal analysis as part of our the analysis when we send it to the lab. One of the interesting things that you'll see here is the amount of iron in paraphyton tissue, again at river mile 6.5. I don't know if anybody's had a chance to go down to the creek down here, but you can see there's a lot of iron flocculent on the stream bed. And we suspect that has a lot to do with what the upstream water chemistry is and the influence of groundwater. And that's something I won't get into now, but it's something we're going to be looking at here in the coming months. One of the other interesting things is copper, and I'm not exactly sure if it's in relationship to urbanization or not, but we see some of the highest copper concentrations in paraphyton at the upper watershed. As you can see, it still increases as you move downstream. And here my last bit of data comes from our nitrogen, or nitrate probes that we have set up at the top and bottom of the watershed. So this is basically a comparison of, in green, what the concentration is at the Canadian border, and in red, the concentration is coming out of Bertrand. So if you look at it in terms of yearly annual concentration, it doesn't look like there's that much of a difference. But when you take into account flow and calculate loading, you see that we have about 63 tons of nitrogen coming in, and you have about 200 tons of nitrogen coming out. Again, that's over a year. And I can't, at this time, put that in context, whether or not this is too much or too little. And I also want to mention there are a few places that we're not accounting for. There's several ditches, trans-border ditches that come in from Canada, as well as Cave Creek. And what we're accounting for is coming in, is just coming in here on the main side. So what's our next steps? One is to build partnerships. There's a lot of data that's being collected in the watershed. I know about a little bit of it. I don't know about most of it, but there seems to be a lot of good opportunities here for people that are collecting this data to be able to get together and share it. I don't know everything, even though I tell my kids I do. I don't know a lot about even some of the information that we're collecting, but that's the reason why we talk to other people, other scientists, and then Markus will be up here and talking about some of the results there today. Another thing is the land is in cooperation with the landowners, because although I have a garden, I come sort of from a farming background, I have no idea how some of these practices work. I don't live in the watershed, I live down in Olympia, and so I'm not as familiar with what people have seen or what people are seeing. So that kind of information is important. Being able to relay this information back to people, so it actually makes sense when they're listening to us, and it also sparks things that they can do, or folks can do to improve water quality and fish habitat. Again, we need to get more of a complete picture. We still haven't monitored any of the tributaries. All of our work is focused on the main stem. The previous talk mentioned some issues over time with flow and urbanizations. It's one of the things that we actually have noticed at the Homer flow station is that we've had an increase in 2007 of the number of high pulse concentrates that have happened, and it's statistically significant. High pulse count definitely has a direct relationship on fish and bugs in the stream. And then again is get this information into such a way that we can develop tools that help people make decisions that are data driven. So whether that's having our continuous monitoring stations available for people to see, data summaries, metrics for people to look at, to meet goals like tons of nitrogen per year, reductions or improvement in fish habitat, that is what the next step is. Let's put some parameters up there that we think we can improve, and let's set some goals for those parameters. And so with that, I'm going to skip by my question part and have Markus come up here and talk about watershed, or the water quality.
Okay, I'm going to try to get through the learning curve portion of this presentation. So let's see here. Scott, I applaud you for going through that. And now I'm going to learn from your example here. Okay. I really appreciate everybody coming out here. This is amazing. I mean, these conferences are so important. I mean, this is what brings us all together and how we can make some changes and to kind of look at things from different disciplines that we're all involved with. And this is where it all happens. It happens in places like this. And basically, just a little bit of background myself. I started working with Scott back in 2008 doing effectiveness monitoring and ecology. And it's been kind of that exploration. We've been working together for a long time. So we kind of have done a lot of projects together. Mainly, he does more of the effectiveness monitoring side, and I am working on the water quality side of things. And we work together both in the same overall program. Oh boy, yeah, there we go, thanks. And then, but I primarily specialize in the water chemistry side. Well, we provide resources and more or less tools and also equipment to actually monitor various different stations in this watershed. And one of the things I wanted to talk about is how is the overall water quality doing? As Scott mentioned earlier, we need tools to actually communicate like overall these complex subjects dealing with water quality. It's not a very easy issue to look at it scientifically because there's so much dynamics going on between chemistry, between flow, between seasons and events. How do we actually know what's going on overall, and how can we communicate these concepts to everybody, to landowners, to educators, to citizens in the watershed, to other scientists, for example. But I just wanted to kind of give a basic idea of what we're seeing primarily in the watershed, and kind of a little bit history of our program. And we're going to go a little bit into that this afternoon to show you kind of the methods that we use to sample and how we actually use our data. And this is kind of what I want to start with primarily is we collect data usually on a monthly level. We have several different stations in the watershed itself, in what we call the Mid-Sac watershed. And we've been collecting for almost 25 plus years now, and at various different sites. These two stations in the Bertrand watershed are actually very new to us. I mean, they are on a completely different system. They're smaller streams as compared to usually we monitor very big systems. We're talking at least 3,000, 4,000 CFS at the lower parts of the watershed. So there's a difference in dynamics here. But what we do is we qualify our data. We sample for all types of different water quality parameters like nutrients, sediment, pH, and conductivity, and temperature. Some is discrete, some single samples per month, some is continuous. But what we try to do is we're trying to actually figure out a way to communicate overall what each of these parameters are doing to an overall water quality score. which we call a water quality index. And what that is it's a ranking system, an indice that you can qualify water quality overall at a given site between a score of 0 to 100. And 0 to 40 meaning poor water quality, so we can give them individual classes. And then 41 to 79, moderate water quality, and then usually 80 to 100, which means very good water quality. And that actually falls within our state standard criteria. Oh, this works. Basically, so what we're looking at is for the parameters that actually have a state standard or a criteria, we usually like put a score of 80. That's actually the criteria. So what the sample we collect, does it fall within that criteria? If it does, then we kind of regress it through a regression equation. We do a series of statistical steps. And basically for set parameters, we have what people coliform. Now, people coliform is variable for different water bodies, and there's different special cases. For pH, dissolved oxygen, and temperature, those are pretty fixed. I think for the DO for now on Bertrand is actually 9.5 milligrams per liter. That is actually the standard criteria. For other parameters in which we don't actually have state water quality standards, and that is phosphorus or nutrients and sediment alone. And that has been a long road. I mean, we are still trying to figure out ways of developing some type of nutrient standard statewide, but we're still working on it. And many systems, and there's a lot of reasons for that. I won't get into that, but I would love to talk about after lunch probably. But what we're trying to do basically in this exercise is we will usually take, with non-criteria scores, we'll just take what is the historical distribution of the data, what is the history of the data, and then in terms of concentration, usually the net nutrient concentrations that are actually in the lower 20th percentile. So more the lower concentrations will fall up in the 80 score level. And then as nutrient concentrations increase, as we see with the distribution of the data, then we'll qualify higher concentrations at lower scores, usually. But when we actually use this, this gives us kind of a way of measuring, kind of putting all those separate parameters together, kind of give us this overall view of a water quality score, which I'll demonstrate very shortly. One of the main things that what we do is prior to setting up stations in smaller stream segments within a larger context of the watershed. So within the Nooksack watershed alone, we have 5 stations that have a large historical context. 2 that right now on the Bertrand are fairly new. We started monitoring that about a year and a half. The oldest site that we actually have where we've been collecting information is the Nooksack at Brennan. And Brennan is a very, very long-term site, over 20 plus years worth of data. It's located roughly on the confluence of the Nooksack going into the Bay. And this is a very important station for us because before you look at the effects of a watershed up in the upscale, what we're doing up in the upper parts, you kind of want to know what's going on cumulatively at the bottom part of the watershed. Because this particular station hydrographically is connected to all stream segments within the Nooksack region. So we kind of want to know what is the overall cumulative effects and how we can compare that to the rest of the Puget Sound, for example. So we usually collect on our sample runs at the same time as Bertrand. We will collect samples below. So when we actually look and break this down into a context, and this is basically the overall water quality score for the Nooksack at Brennan from 1995 to 2013. We usually kind of monitor, we break it up in segments between 5-year trends, 10-year trends, and 20-year trends. And what we've been noticing, actually, this is a pretty consistent score. It's of 58. So we're doing moderate. So moderate water quality has been prevalent in this region for about 20 years, roughly. But one thing that what we like to use the indice for is we want to look at individual parameters. What is driving those scores to 50? Well, why is it staying consistent? And so what we look for is when we break it down, for example, the polyphonic, the oxygen, the pH, the total sediment, temperature, nitrogen, and phosphorus, and turbidity, we're noticing that the nutrients parameters and actually the sediment parameters are keeping those scores consistent with the 50. So, and these are very low scores. These are in the 40s. So for water quality, in terms of sediment, and then nutrients in general. So This gives us an idea. Okay, so we have a nutrient sediment dynamic that could be possibly happening within the upper parts of the watershed. So we take a look at the two weather stations. And here's another example. We have the topmost station is actually Bertrand at Avenue 0, Bertrand at Rathbone, and then there's the lower station at Brennan. They're all scoring in a very similar way. Brennan, of course, is at 58, Rathbone's at 53, and Bertrand at 0 is 51. So, but then again, we take into context. Here's a photo, okay, of the Brennan site. It's a very large system, and when it rains, it's very flashy. We get a lot of change in hydrology. But if you look at the smaller sites, they're very confined, small stream channels. They don't get a lot of CFS, but we do see the same dynamics that are actually happening. So if we were to take the water quality scores and just lay them out as box plots, so we're showing annual distributions of all the data that we've collected so far. Block it out per parameter for people coliform oxygen, temperature, pH, to nitrogen, phosphorus, sediment. What we're seeing in the actual parameters with criteria, such as fecal coliform oxygen, temperature, pH, there's not much difference between all three sites. Actually, we're seeing fecal coliform is always going to be a variable issue. Oxygen, usually between the upper and lower sites, the variability is pretty much the same, except that the midsection in Rathbone, we're actually seeing more of going out of these standards when the summer period actually happens with temperature. So, but when you want to come and take a look at this, as with the previous talks, as Scott pointed out, we have a huge fluctuation in nutrients and sediment. The upper portion of the watershed, we're seeing less amount of nitrogen. However, with phosphorus and sediment, a little bit less. But when you get into the midsection of the watershed at Rathbone, we're seeing more diversity, more distribution of sediment, more distribution of nitrogen, heavier loading. And then it dissipates out at the bottom part of the watershed where it actually dissipates. So obviously, some type of biological processes are using the nitrogen and recycling. So just to give you an idea, yes, we do see sediment dynamics. It's very, very prevalent. And a lot of other studies actually are in the process of quantifying that, including the USGS. We're short. So I just want to, I got 1 minute left, and so I will talk to you later this afternoon about what we do out in the field.
Okay, thank you.